we have an axial load of 80 kilonewtons applied on a rectangular bar of length 1.5 meter or 1,500 millimeters. X cross section is 100, Y is 50 millimeter. Young's modulus is a steel bar, so Young's modulus is 200 gigapascals. Poisson ratio is 0.32. As I mentioned, the metals have a Poisson ratio around 1/3. What is the change in length? The 80 kilonewtons we apply, we're assuming that it is in the elastic range, so the Hooke's law applies. So we're looking for axial extension or extension in Z direction along the applied load. Part B, change in lateral dimensions. Change in X, that is delta X, and change in Y, delta Y. What is delta X and delta Y? Hooke's law applies, as I said, the deformation is restricted to elastic region. That's why we can use uniaxial extension formula, PL divided by AE, where P is the load, L is the length, A is cross-sectional area, E is the Young's modulus. Now, I solved this in two different set of units to give you the perspective on that. For the first one, I used the dimensions in millimeters, and in the second one, I use the dimensions in meters. 80 kilonewtons is 80,000 newtons. 1.5 meters times 10 to the 3 in millimeters. So newtons and millimeters in the numerator. Cross-sectional area, we should stick to millimeters as well. So 100 by 50 millimeters. That means Young's modulus, 200 gigapascals. Then we got to convert it to megapascals, which is newtons per millimeter square. And this is in millimeters square, so they cancel out. The numerator becomes in newtons. That is newtons. Newtons cancel. And what you have is millimeters. Is 0.12 millimeter is the change in length. Let's use meters for the same 80,000 newtons. Instead of millimeters, we use 1.5 meters as the length divided by the cross-sectional area, which is 0.1 by 0.05. But this time we have to express the modulus in pascals, which is newtons per meter square. Okay, that is newtons per meter square. And this is meters square, and they cancel out, and that is meters, and that is newtons. Newtons cancel out, so the answer would be in meters. And so 1.2 times 10 to the 4 meters, and multiply that by 10 to the 3, and you get 0.12 millimeters. Same as above. You can just use the millimeters or the meters approach. It's a very small extension considering how big the force is. Let's look at the part B, which is the change in lateral dimensions of the specimen. So let's consider the definition of Poisson ratio, which is minus lateral strain divided by the axial strain. What are lateral strains? Epsilon x. What is axial strain? Epsilon z. Because of isotropy, that is equal to epsilon y divided by epsilon z. Okay, isotropy means there's no direction dependence on the strain. Epsilon x divided by epsilon z, negative. Negative epsilon y divided by epsilon z. Considering isotropy, epsilon x is equal to epsilon y. So that is minus nu epsilon z, as you see in this representation. Epsilon x is equal to epsilon y, and that is equal to minus nu. Epsilon z is change in length divided by original length. Substituting these values, minus 0.32 times the change in length we calculated already in the part A, which is 0.12, divided by original length 1,500 millimeters. We use millimeter in both. If you use meters here, you would have to use meters in the denominator. Calculation gives rise to minus 2.56 times 10 to the minus 5 as a strain. There is no unit, millimeters by millimeters, no unit. for the strain. Epsilon x is equal to change in the length in x direction divided by original length. Original length is 100 millimeter, and strain we calculated. So from here you find the change in length as 2.56 times 10 to the minus 3 negative. Negative signifies contraction. 10 to the minus 3 millimeters is a micrometers. Similarly, epsilon y is change in length of y dimension divided by original y dimension. The original y dimension being half the x dimension. Change in length in y direction is when you multiply by strain. Instead of 100, you have 50. You get half the value to 1.28 micrometers is the change in y dimension. In summary, we have extension of 0.12 millimeter and contraction of minus 2.56 micrometer by minus 1.28. Negative signifies and indicates contraction. So we have in this bar, to summarize, we have 80 kilonewton or 80,000 Newton applied to our bar, rectangular bar, 1.5 meter length, 100 by 50 millimeter cross section. Young's modulus is 200 gigapascal or 200 times 10 to the 9 pascal, and Poisson ratio is 0.32, gives rise to changing length of 0.12 millimeter, much less than a millimeter extension, and the contractions in x and y dimensions minus 2.556 micrometer and 1.28 micrometer respectively. This is in micrometers, this is in millimeters.